Modern physics suggests that gravity is exactly 0% a force between objects. Research from Princeton University confirms that mass dictates 100%, but your body feels this curvature as a physical weight pinning you to the Earth right now. This paradox haunted Albert Einstein until he witnessed a man plummeting from a roof in 1907. Einstein realized that a person in freefall feels no weight, finally proving that gravity is merely acceleration. For 8 years, he obsessed over this insight, wrestling with the complex mathematics of non-Euclidean geometry and the tensor calculus of Marcel Grossmann until he could finally prove that Newton's invisible pull was a total illusion. In November 1915, standing before the Prussian Academy of Sciences, Einstein unveiled his General Theory of Relativity, and the foundation of the world shifted forever. He taught us that we have to stop thinking about gravity as an invisible rope connecting the moon to the Earth. Instead, imagine space and time as a vast, four-dimensional fabric, a physical entity called spacetime. Think of it like a taut trampoline. If you place a heavy lead weight in the center, the fabric stretches and dips, creating a valley. If you try to roll a marble across that trampoline, it does not travel in a straight line. It naturally follows the curve toward the heavy object. That is exactly what is happening to you right now as you sit in your chair. You are not being yanked toward the floor by some mysterious Newtonian string. You are simply caught in a well of geometry. The Earth is so massive that it warps the very space you occupy, turning every straight path into a curve toward the planet's center. This was not just a clever mathematical trick or a pretty metaphor. The human story of this discovery climaxed in May 1919 during a total solar eclipse. The British astronomer Arthur Eddington, a man who understood the profound implications of Einstein's work better than almost anyone in the English-speaking world, led an expedition to the island of Principe, while a second team led by Andrew Claude de la Cherois-Cromelin headed to Sobral, Brazil. They were there to test a radical prediction. If gravity is truly the curvature of space, then even light, which has no mass, must follow those curves. As the moon blocked the sun's glare, Eddington photographed the stars, visible near the solar rim. When he compared those plates to photos taken of the same stars at night, the positions had shifted. The sun's mass had bent the starlight itself. It was the moment Einstein became a global icon. He had revealed that the force of gravity was a lie. We do not live in a universe of tugs and pulls. We live in a world of slopes and curves, where the very stage of the cosmos is alive and bending under the weight of the stars. In Einstein's world, the ground is not pulling you down. It is pushing up against your feet, preventing you from following your natural curved path through the warped geometry of the room. Now, imagine you are sitting in the drafty halls of Trinity College, Cambridge, back in 1687. You are watching a man named Isaac Newton struggle with a problem that should have been impossible. Newton didn't just want to know why an apple falls. He wanted to know why the moon stays in the sky. He gave us the Philosophiae Naturalis Principia Mathematica, and with it, he turned the universe into a giant, predictable clock. He treated gravity like an invisible tether, a cosmic string connecting every mass in the existence. He gave us the Newtonian constant, that big capital G. Even with our best technology at NIST in 2024, that number, 6.67430 times 10 to the negative 11th, remains one of the most elusive figures in science, with a relative uncertainty of 2.2 parts in 100,000. Newton's math was so good that we still use it to define standard gravity at 9.80. It's the math that brings our astronauts home. But here is the secret Newton whispered to his contemporaries. He famously said, "Hypotheses non fingo. I frame no hypotheses." He could tell you how gravity moved the planets to the 4th decimal place, but he confessed he had no idea what gravity actually was. To him, the idea that a rock could feel the pull of a planet across millions of miles of empty vacuum instantly and without any, he called it action at a distance, and it bothered him until the day he died. He handled the how with genius, but the what remained a ghost in the machine. For 2 centuries, we lived in Newton's clockwork world, and it felt safe. But as we moved into the 20th century, the gears began to smoke. While Einstein was busy reimagining space as a flexible fabric, a new generation of rebels, men like Werner Heisenberg, Niels Bohr, and Richard Feynman, were looking at the world of the very small. They were building quantum mechanics, a theory where everything is quantized or broken into little chunks. In the quantum world, things don't slide smoothly. They jump. Everything they believed up to this point was wrong. You see, we have run into what we call the incompatibility crisis. On one hand, you have general relativity, which describes the universe as a smooth, continuous, beautiful velvet cloth. On the other hand, you have quantum mechanics, which describes the universe as a jittery, chaotic pile of Lego bricks. When you try to use the math of the smooth cloth to describe the Lego bricks, the needle breaks. Specifically, when you try to calculate the gravitational force at the center of a black hole or at the moment of the Big Bang, the equations start spitting out infinity. In physics, infinity is just a polite way of saying your theory has failed. It's like trying to play a classic vinyl record on a turntable made of sandpaper. This leads us to the most embarrassing number in the history of science: the cosmological constant problem. When quantum physicists try to calculate the energy of empty space, the vacuum energy that should be exerting a gravitational pull, their math is off from the observed reality by that is a 1 followed by 120 zeros. It is the worst theoretical prediction ever made. And then there is the weakness problem, or the hierarchy problem. I often tell my students to think about a simple refrigerator magnet. Think about it. The entire Earth, 6 sextillion tons of iron and rock, is pulling down on a single paperclip with its full gravitational might. And yet, you can reach down with a tiny 2-cent magnet from a souvenir shop and lift that paperclip up. Your tiny magnet is winning a tug-of-war against the entire planet. That is because gravity is roughly 38 orders of magnitude weaker than electromagnetism. Why? Why is the force that holds the galaxies together so incredibly puny compared to... We are currently standing in the middle of a scientific schism. We have 2 perfect maps of reality, but they don't share the same language. We can measure the weight of a mountain and the orbit of a star, but we can't explain why a single atom feels the pull of the Earth in a way that fits our quantum equations. We have the clockwork, but we've lost the key to the mainspring. By the spring of 2026, the way we listen to the universe had fundamentally shifted. For over a century, we were like people trying to understand a symphony while wearing heavy earplugs, only able to see the frantic movements of the conductor's baton. But on March 5, 2026, the LVK collaboration, the global network of the LIGO, Virgo, and Cagra observatories, released the GWTC4 catalog, and it was as if someone had finally handed us the sheet music. This wasn't just an incremental update, it was a census of cosmic violence. They confirmed 128 new gravitational wave events in a single release, bringing our total library to roughly 350 detections since that first historic chirp was recorded back in 2015. Among these detections was a record-shatterer labeled GW231123. This was the catastrophic merger of a binary black hole system where each participant was approximately 130 times the mass of our Sun. When these 2 behemoths collided, They didn't just release energy, they shook the very geometry of the vacuum. Imagine space-time as the surface of a drumhead. When those black holes danced, they sent ripples through that drumhead that traveled across the void at the speed of light. By the time they reached our detectors on Earth, the displacement was smaller than the width of a single atomic nucleus. And yet, our technology is now so sensitive that we can hear the fabric of reality stretching. But here is the puzzle that keeps us paced in the corridors of Stanford and MIT. Why is the force that moves galaxies? You don't believe me? Look at your own life. You can pick up a paperclip with a tiny 5-cent refrigerator magnet. In that moment, the electromagnetism in that little piece of ceramic is successfully winning a tug-of-war against the entire gravitational pull of the planet Earth. All 6 sextillion tons of Earth's core, mantle, crust, and oceans are pulling down on that paperclip, and they lose. They lose to a magnet the size of a thumbnail. Physicists call this the hierarchy problem. Gravity is roughly 10 to the power of 40 times weaker than the electromagnetic force. That is a 1, followed by 40 zeros. To bridge that gap, you'd need an analogy involving the size of a single atom compared to the diameter of the entire observable universe. Because gravity is such a light sleeper, measuring its fundamental strength, the Newtonian constant, or big G, is a nightmare. As we approach the December 31st, 2026 deadline for the next codata adjustment of physical constants, the physics community is in a currently, G sits at roughly 6.67430 times 10 to the power of minus 11 cubic meters per kilogram per second squared, but its relative uncertainty is nearly 1,000 times greater than that of the charge of an electron. It's the wobbly leg of the table of physics. We can calculate the orbit of a satellite with GPS-level precision, which, by the way, requires accounting for the fact that time itself ticks faster as you move away from Earth's mass. Yet we still struggle to define the exact strength. The plot thickened in early 2026. Just as researchers at the University of Waterloo were proposing a quadratic quantum gravity model in March 12th's Physical Review letters to finally hunt for primordial gravitational waves, another bombshell dropped. A study from the University of Bremen suggested that the accelerating expansion of the universe, the thing we've been blaming on dark energy for decades, might actually be an illusion caused by the extended geometry of space-time. It suggests that gravity doesn't just curve space. It might be playing a much deeper, more deceptive game with the very definitions of distance and time. We see the ripples. We calculate the mass of 130 solar mass black holes, and we predict the 9.8 meters per second squared acceleration of a falling apple. But as the 2026 Codata meeting at the BIPM looms in September, we are forced to admit a humbling truth. We are measuring the shadow of a ghost. The year was 1983, and in a small, cramped room in San Francisco, Leonard Susskind felt the floor falling out from under him. He wasn't experiencing a localized gravitational anomaly. He was listening to Stephen Hawking. Stephen, in his characteristic synthesized voice, had just proposed something that felt like He claimed that if you threw a book, say, the Feynman Lectures, into a black hole, and that black hole eventually evaporated through the quantum process we now call Hawking radiation, the information in that book was not just hidden, it was erased from the universe. This was the opening shot of what Susskind would later call the Black Hole War. To understand why this matters, you have to understand that in physics, information is the ultimate protected class. If you burn a book in a fireplace, the information seems lost, but it's actually just scrambled into the ash and the rising smoke. If you had a powerful enough computer, you could theoretically reconstruct the pages. But Hawking was saying gravity was the ultimate cosmic shredder. If the information was truly gone, then the fundamental rule of quantum mechanics, unitarity, was broken. Science itself, the ability to trace the present back to the past, would vanish. Susskind spent the next 2 decades in an intellectual fever dream, often pacing his home or the halls of Stanford, trying to figure out how gravity could be so cruel. He teamed up with the brilliant Dutch physicist Gerard 't Hooft, and together they began to suspect that our entire understanding of how gravity occupies space was wrong. They realized that a black hole wasn't just a bottomless pit or a bathtub with the drain left open, as we often imagine it. Instead, they proposed something that sounds like pure science fiction: the holographic principle. Think about the hologram on your credit card. It's a 2-dimensional sticker, yet when you tilt it, you see a 3-dimensional image. Susskind and 't Hooft argued that the 3D interior of a black hole, everything that fell in, was actually stored as bits of information on the 2D surface of the event horizon. Gravity wasn't just pulling things in, it was flattening them out into a cosmic code. But the most shocking, in 1997, a young physicist named Juan Maldacena at Harvard provided the mathematical smoking gun that Susskind needed. Maldacena showed that a certain type of 5-dimensional universe with gravity was mathematically identical to a 4-dimensional universe without gravity on its boundary. This is what we call the ADS/CFT correspondence. It was the moment the war shifted. It suggested that gravity itself might not be a thing at all, but an emergent illusion created by the entanglement of information on the walls of the universe. This is the ultimate Susskind-esque irony. We spent centuries trying to figure out what gravity is doing to us, only to realize that gravity might just be the way our 3D brains perceive a much simpler 2D reality. In 2004, at a conference in Dublin, Hawking finally stood before his peers and conceded the bet. He walked onto the stage and admitted that information is preserved. He gave his opponent, John Preskill, a baseball encyclopedia as a prize for winning the wager, though Stephen joked that the information in it was useless. The war was over, but the victory left us with a reality that was stranger than anything we had imagined. Gravity, the force that feels so heavy and real when we trip and hit the pavement, might actually be the ultimate cosmic projection, a holographic shadow cast by a deeper, quantum layer of existence that we are only just beginning to decode.